Hello friends, and welcome to my little corner of the matrix. We're going to talk about statements and the negation of statements for our first video on logic. And here we go. It is convenient to think of a statement as a truth-valued function. We refer to a statement as truth-valued because it is either true or false, and has a value of t for true and f for false. Why we refer to a statement as a kind of function will become more clear as we press onward. For now, it should suffice to say that the veracity of certain statements are contingent upon the veracity of the parts of that statement.
Hey, you. Hey,
fuck.
Where you go?
Sorry about that. So, for now, it should suffice to say that the veracity of certain statements are contingent upon the veracity of the parts of that statement. Alright, moving on. If we let P denote a statement, then we denote the negation of P by tilde P. That stands for not P. Not P is defined to be true when P is false, and false when P is true. Alright. Note that the truth value of not P is dependent upon the truth value of P. This is why we refer to not P as a function. It's a function of P. That being that it depends on the value of P, much in the same way that functions in algebra depend on a variable x. Alright, for example, let P denote the statement, the sky is blue. Then not P is, the sky is not blue. Or not P is, it is not the case that the sky is blue. Okay. So now let's talk about logical and or operators. In logic, there are two commonly used binary operators, and or. Let P and Q represent two statements. Then these operators are used in the following manner: P and Q and P or Q. For example, P is the sky is blue, and Q is the grass is green. Then P and Q would be the sky is blue and the grass is green. P or Q would be the sky is blue or the grass is green. So, P and Q is defined to have a value of t for true when both P and Q have a value of t, and false otherwise. P or Q is defined to have a value of t in the event that P has a value of t, and in the event that Q has a value of t. Note, using the and or operators on P and Q results in two new statements: P and Q and P or Q. The point is that they're statements, right? They're also truth-valued functions. So, moving on. The truth value of each of these statements depends on the truth value of the operands, P and Q. Furthermore, since no statement can be simultaneously true and false, we may regard these statements as functions of P and Q. Also note, it is not necessary for both P and Q to be true in order for the statement P or Q to be true. P or Q is true in these cases: when both P and Q are true, when P is true and Q is false, and when P is false but Q is true. That is, the statement P or Q is true when at least one of P or Q is true. For example, P is the sky is purple, and Q is the grass is green. Then P and Q is the sky is purple and the grass is green, and P or Q is the sky is purple or the grass is green. Now, notice that the sky is purple is false. I think we can agree that it's false. Maybe. Q, the grass is green, is true. I think we can agree that's true. Assume it's a well-kept, I guess, front yard. The grass is green as opposed to brown. Then the statement P and Q, the sky is purple and the grass is green, would be false. Why? because in order for the statement P and Q to be true, both P and Q must be true, but P is false. So, yeah. However, the statement P or Q, the sky is purple or the grass is green, is true, because Q, the grass is green, is true. And it doesn't matter that P, the sky is purple, is false, because we only require that at least one of P or Q is true. Yeah, there we go. Moving on. Now let's talk about the negation of statements involving the and/or operators. You might be wondering what the negation of the statements P and Q and P or Q might be. The answer to this question is a result commonly known as DeMorgans Laws. Bum bum bum. Yeah. Here's DeMorgans Laws. Part 1 says that not P and Q is equivalent, interchangeable with, whatever, not P or not Q. And Part 2 says that not P or Q is equivalent to not P and not Q. Note, the double arrows indicates that under the same conditions, i.e. for the same values of P and Q, the statement on either side of the double arrow has the same truth value as the other side. In practical terms, either side of the double arrow is interchangeable with the other. Next, we will undertake to prove DeMorgans Laws by using a truth table. We will only prove Part 1, leaving Part 2 as an exercise for you, the viewer. Lucky you. Okay, so here's the truth table. This is what it looks like. And so in the columns for P and Q, what we've done is we have laid out all the possible combinations of truth values for P and Q. So in the first, or actually I should say the second row, we have both P and Q being true, and then in the third row we have P is Q and Q is false, excuse me. The fourth row we have P is false, but Q is true, and in the last row we have them both being false. And what we're going to do is we're going to fill out the other boxes based on these combinations of the truth values of P and Q. Here we go. There we go. So now we've computed the values of not P and not Q for all the combinations of the truth values of P and Q. How do we do it? Okay. Hold on a second here. Okay, so the idea is that not P is true whenever P is false, and not P is false whenever P is true. So basically what we have here is not P is the mirror, or is the opposite of P. And so we've laid out all of those values in the third and fourth columns. Alright, moving on. We want to compute the truth values of P and Q, or the statement P and Q. Here we go. There we go. So it goes true, false, false, false. And this makes sense. But we want to note that we evaluate P and Q using the values of P and the values of Q. That's what we're doing. We're going to use the values of P and the values of Q to evaluate the statement P and Q. Okay, here we go. So in the second row, we note that that combination has P being true and Q being true. And so since they're both true, then P and Q, by definition, is true. And then in every other instance, the third row, right, it's false. The fourth row, it's false. In the fifth row, it's definitely false, because in those rows there are some combination of either P or Q being false, and the last row being P and Q being both false. So there you go. Now we're going to compute the truth value of not P and Q. Let's do that. And there you go. It goes false, true, true, true. How do we get that? We computed the value of not PNQ by looking at the value of PNQ. Because it's not PNQ, it should have the opposite truth value of PNQ. That is, when PNQ is true, not PNQ is false. And then in the third row, when PNQ is false, not PNQ is true. And then in the fourth row, when PNQ is false, not PNQ is true, of course. And then in the last row, when PNQ is false, again, not PNQ is true. Surprise. All right. Last column, this is what we were aiming for. There we go. It's false, true, true, true. Okay? How do we get those values? We got those values by using the values of not P and not Q, as you'll see. Okay, so we're computing not P or not Q. Here we go. So when both not P and not Q are false, then not P or not Q is false. Right? Because in order for it to be true, we have to have at least one of not P or not Q being true. But in this case, they're both false. So not P or not Q is false. Okay, in the third row, we have not P is false and not Q is true. And since we have at least one of not P or not Q true, man, that's a tongue twister, then not P or not Q is true, right? Because not Q is true, right? We just need one of them to be true for this statement to be true. Then in the fourth row, we have not P is true. And so then automatically, maybe not automatically, but, well, yeah, okay. Then the statement not P or not Q is true, because not P is true. And the last row, both not P and not Q are true, and so therefore the statement not P or not Q is true. Yeah. Okay. And so what we're looking here is we want to recognize that the last two columns, right, the second to last column for not P and Q has the same sequence of truth values that the last column, not P or not Q, has, right? The same sequence. It goes false, true, true, true. And what this indicates is that under the same conditions, that is for the same values, truth values of P and Q, not P and Q and not P or not Q have the same truth values. That is, you get the same result. If you plug in the same truth values for P and Q, they give you the same results. In other words, they're the same, right? They're equivalent, right? Is what this means, and that's what we were aiming to prove. And so we conclude, since not P and Q and not P or not Q have the same truth values for the same truth values of P and Q, we conclude that part 1 is valid. QED. There we go. That's success right there. All right. So let's move on. Okay. There's DeMorgans Laws, and now let's see what DeMorgans Laws tell us about our previous example. So there's the previous example that we had going. We have P is the sky is purple, ridiculous. Q is the grass is green, true, maybe. We have P and Q, the sky is purple and the grass is green, ridiculous. We have P or Q, the sky is purple or the grass is green. And they have the values, the truth values, false, true, and true, respectively. Okay. Now we have let's compute not P and not Q. So not P is the sky is not purple, and not Q is the grass is not green. And not P would have the value of true, because the sky really isn't purple, usually. And not Q is the grass is not green, which hopefully isn't true, so false, right? Well, yeah, okay. Remember, we're talking about a well-kept front lawn. Someone who's been watering the grass, right? It's a green lawn, so it definitely is green. Okay. Note, since our previous example resulted in P and Q, the statement P and Q, being false, and the statement P or Q being true, we expect the negations, not P and Q, and not P or Q, to be true and false, respectively. That's what we expect, right? Because not P and Q should have the opposite truth value of P and Q, and not P or Q should have the opposite truth value of P or Q, right? So this is what we're expecting to get using DeMorgans Laws. So there's not P and Q, and then there's not P or Q. And then, by DeMorgans Laws, right, we substitute. We use not P or not Q, and not P and not Q, right? So we've just made a simple substitution because they're equivalent. By DeMorgans Laws, they're equivalent, right? And so we're going to see what truth values those two statements yield. Okay. So here, not P or not Q is the sky is not purple, or the grass is not green. And not P and not Q is the sky is not purple, and the grass is not green. What truth values might those have? Well, not P or not Q is true, and not P and not Q is false. Okay. And how do we compute those values? Well, see, it's because not P is true and not Q is false, right? So we note that we evaluate not P or not Q and not P and not Q with not P and not Q, right? So we use those values and we plug them in to our and or expressions to compute what is the truth value. And that's how we got the value of true and false for not P or not Q and not P and not Q respectively. Hello. Okay. And we want to note that the truth values, right, are opposite, right? P and Q has a truth value of false up above there, while not P or not Q has a value of true. And P or Q up above that reads the sky is purple or the grass is green has a value of true, whereas not P and not Q, the sky is not purple and the grass is not green, has a value of false. It's important to note that this is merely a confirmation of what we already knew. Right? We already knew that if P and Q is false, then not P and Q would be true, right? And we already knew that if P or Q is true, then not P or Q is going to be false. We already knew that. So we've merely confirmed that fact using DeMorgans Laws. So, here are some exercises for you to do. Number 1, construct a truth table to verify part 2 of DeMorgans Laws. You should be able to do it just like I did it by constructing a little table. Yeah, just do it. Do it just like that. And number 2, use DeMorgans Laws to find the negation of that gross expression. Part 3, in common usage of the word or, in common usage, the word or often indicates that one statement or another is true, but not both. For example, the statement, you will get good grades or you will fail the class, probably means that either you will get good grades or you will fail the class, but not both, usually, right? come up with a formulation in terms of P and Q and our and/or operators that captures this particular meaning of the word or, right? This is called an exclusive or, right? And there is a particular symbol for an exclusive or, but I can't find it. I can't find it in my library of symbols. Anyway, it's out there. You can Google it. Anyway, so do these exercises, and we'll see you next time.